We've been working on quantum computers for the last almost 10 years, although in the last couple of years we've kind of dropped the ball a little bit. It's one of those projects that, research is advancing, applications are rare, and interest is waning. We just wrote an essay about CRISPR concerning that type of scientific project that doesn't really yield results. Unfortunately, quantum computing is in the same realm, although there are green shoots. There are things that, in our opinion, could lead to real applications. And today's episode is interesting for two reasons. One is there is actually one of the researchers that we're discussing that, in my opinion, has an interesting approach. The links are in the show notes with all the papers and the names. I don't want to, spend my time mispronouncing names here. So, let's call it researcher one. And then researcher two actually is doing the opposite. And that's really interesting. And the title of this episode is AI for Quantum and Quantum for AI, because he's kind of flipping the whole thing on its head. He's using neural nets to approximate quantum materials. So he's using our current classical technology of accelerated compute and neural nets, or universal function optimizers, to approach the multi-particle dimension, high dimension interaction problem that material science poses. He's a condensed matter physicist, and he's trying to understand, like every other material science physicist, I think, how do materials actually, how can we design materials from first principles? And the goal being, imagine if we could inverse design, if we could prompt a property. For example, I want to have a tile that can withstand re-entry of orbit for Starship, and then the AI can actually offer me some options, some material options that we can use, and then we can still maybe do some fine-tuned research in the lab, in the wet lab, if you will. But we can, in digital space, reduce the action space to the point where we can actually really do very efficient research. So that's the idea fundamentally. The reason I think this episode is interesting, in my opinion, is because we're looking at AI for quantum. So that would be the first approach. So researcher one, who is using AI. Excuse me, that's actually researcher two. So this particular material science physicist, he's using AI to understand quantum better. And then quantum for AI, researcher one, he's using quantum computers to accelerate AI. This is not even on podcast. It's March 11, 2026. This is Karim Belko. For the year, we're down 8.2%. The market is down 0.5%. We're underperforming by 8.7%. So let me, before I go into the actual presentations, just talk a little bit about quantum computing in general. So quantum computing is the idea that we can use a substrate of physics that follows quantum mechanics and doesn't decohere. So has particularly three interesting properties: superposition, interference, which is kind of the same, and then entanglement. So those are things that we don't have in the classical world. Those are dynamics or properties that are present in the quantum world. At least that's what we call these things that we see. So, for example, the idea that we can have a Hamiltonian or a wave function of a particle spreading out and interfering with other wave functions, and then let's say create superposition to amplify itself or destroy itself, so make it null by being inverse, and then the entanglement thing, the thing that Einstein called spooky action at a distance. That, of course, is that's a whole different ball game, and the idea of a quantum computer is to take advantage of these dynamics to actually do computation. So researcher one is basically solving the non-convexity problem of classical AI algorithms. So you have lots and lots of local optima, right? So the idea is you're a hiker and you're hiking in the Swiss Alps, and your goal is to find the, let's call it, your goal is to find the most beautiful lake. And you're going to go up a mountain, down a valley, and you're going to come to a lake. The lake is always going to be somewhere in a valley, just by definition, because that's where the water gathers. And the problem now is you're standing next to that lake, and you have the option to go up the other side of the valley and maybe see somewhere else if there's another more beautiful lake. Or maybe actually a better problem would simply be, I want to find the highest lake in terms of altitude. And the problem here, of course, is I found the lake and I now have to go back up and then hopefully on the other side back down. But that other lake that is maybe on the other side could be higher or not. So you see the problem here, like iteration can work, but it's very costly. Imagine instead of the Swiss Alps, I have a Hilbert space here. I have almost near infinite valleys and peaks. How am I supposed to know where the actually highest lake is, or lowest lake, or whatever I'm optimizing for? And this researcher one is actually solving or using quantum computation to solve that problem by propagating a wave function across all these mountains and valleys, and then using some quantum algorithmic or quantum computation to interfere with the lake and find also maybe a even better way to formulate this would be to have a valley and a lake interfere, particularly when they're the highest, and then in that way, in one shot, find not just a lake but also the highest lake. This is not a technical podcast, so don't expect me to now go into the details. This is pretty high level physics, and I just want to talk about the idea. And the idea is being to use quantum computation to actually accelerate a non-convex solution space. This is fundamentally the idea. And I think this is something that I would actually subscribe to. So I think coming back to Orange Capital Partners, why are we doing this? Of course, we are actively looking for potential investments in the quantum computing space. And the one problem that we have with this space is, on the one hand, the hardware is, let's say, under-promising right now. Software-wise, it looks better. The problem is the applications. And the problem is twofold. One is that the industry is not able to deliver the kinds of applications maybe that could be breakthroughs. And the other problem is also that the users or the potential users are mainly legacy companies, airlines and power companies and things like that. You will never have a breakthrough in something disruptive with these types of end users. So what we need here is, we need a Tesla, we need an Amazon, we need an NVIDIA, we need a company, an entrepreneur that takes this into their own hands and actually moves forward and not just develops the computational infrastructure, but also builds up the applications. So having said that, now this is a potential speed up for AI and a potential speed up for solving optimization problems. And whenever, in this day and age, if we combine these words, speed up, AI, optimization, there is opportunity. There is absolutely opportunity. And that's why we're talking about this. So we're going to monitor this. I think, again, researcher one, in links in the show notes.
we will definitely keep an eye on it. Now, the second researcher we want to talk about, this is actually the inverse here. So this person is using, and he has, this is a really well-defined project with a researcher who's, I would say, accolades speak for themselves. He's been around for a while. So what he's doing is he's using AI technology or infrastructure such as neural net, transformer architecture to predict quantum materials. Quantum materials are materials that follow topological properties. So they have properties that, for example, topological insulator is the kind of material that has certain in certain configurations is an insulator, in other configurations isn't, and also stays like that with deformation. So those are quantum effects. Again, I'm not going to go into too many details here technically, but the idea, I want to talk about the idea because it's really exciting. So he's using, he's taking fermions, which are electrons. The difference between bosons and fermions is the fermions cannot be at the same time, the same place. Photons are bosons, so they can. So fermions, they follow a certain Hamiltonian. In other words, they follow a certain physics equation, a certain dynamic equation, which is best described by the Schrödinger equation. And he's putting them as inputs into a neural net. He's then using weights to optimize for the lowest energy configuration that the particular input of fermions can have. You put in a collection of fermions or electrons, which are, let's say, certain elements at their fermionic structure. You then optimize their Hamiltonian based on the relationships, so the cross relationships between these elements, using some physics like using symmetry and things along those lines to reduce the dimensionality. And what you're doing is you're letting the network guess, so you iterate by guessing how to achieve the lowest energy state. That's the key. So when I saw this presentation first, I was a bit confused because I believe there is a conservation of learning, like the same way there's conservation of energy. Like you can't learn something out of nothing. Like there has to be a price to be paid. Either you learn from data, or you learn with, let's say in reinforcement learning, in model-free, real-time applied reinforcement learning, you just learn by doing. Experience, but you have to have a certain optimization function, and you have to have, you have to have something that tells the model you're right or wrong, and so it can iterate and learn. And in this case, I guess this right and wrong thing is the energy state at the end of this evolution, and the neural net learns the weights, determine the weights are collectively the function which determines that state. So what this researcher is able to do is, at least in principle, start with a bunch of elements and then produce materials or properties of materials that correspond to a certain desired property of materials. That's the idea. So this is kind of akin to AlphaFold in that sense, that you're starting with a sequence, in the case of AlphaFold, amino acids, and you get to a protein. And here you start with a sequence of elements, and you end up in a state that could be beneficial from a design perspective. So I think in both cases, these are research projects. These are early days, but I think both are very promising in two ways. I think fundamentally they show that there is a computational shortcut that quantum computing can offer, either by actually using quantum computing directly to solve AI problems, or by using those computational shortcuts to, with the help of AI, approximate something that would otherwise suffer the curse of dimensionality. Thank you.